So now we'll be considering applications of signals and systems. And so far, we've been able to treat quite a number of topics, ranging from the basic definitions of what signals and systems imply, okay? So now we want to address applications. So I think that is where we started from. We literally started with the definition of terminologies. So we started off with what a signal is and then what a system is. And the bottom line is we tried as much as we could to make things pretty simple, that, well, a signal is an abstraction of any measurable quantity that is a function of one or more independent variables, such as time or space. So meaning, for us to have a signal, we must have dependent and independent variables. Variable or variables. And then we see how these things interact. And we said, well, our independent variable could either be time or space. And then we said a system is anything that can take this signal, act on it, then produces an output. So it means it's more like some box. It could be a white box, not necessarily a black box, okay? And then we said this system is usually characterized by some parameter, which we want to call the impulse of that system, the impulse of that system. And then once an input acts on it, say S of t, then we should get Y of t, which is either a direct replica of the input or a distorted version. And then we said, well, this output is going to be some product of the input and the property that characterizes this system in the frequency domain. So meaning in the time domain is going to be the convolution. So it means X and Y, so it means Y of t will now be S of t convolved with H of t. We didn't stop there. We also went on to say, well, signals could be either single variable or multiple variables. And I just mentioned either variables, independent variable, or variables, right? And then we also said that these signals and systems could be classified as either continuous or discrete. So it could be continuous time signals, meaning they are literally continuous, or it could be discrete, meaning we could represent them with some points. And this led us to a beautiful world of describing what we could. And then we said, well, designing practical systems could be very difficult, but there should be an approximation to ease analysis. And that was, and that actually brought us to what we call the linear time invariant systems. That's LTI. And then we went on to explain what these LTI systems are. And then just before talking about the systems, we talked about different kinds of signals analog signals, digital signals, real signals, complex signals, deterministic, and a whole lot of other signals, odd signals, even signals. And we also talked about periodic signals, conjugate symmetric signals, neither energy nor power signals. And we try to just explain that, well, this little guy here, which we address as signal, could be interpreted in different ways. But the bottom line is, for us to be able to have an actual practical signal, it must be some complex quantity. Okay? Such that this signal will definitely have the even component and the odd component. Okay? And depending on what is desired or required, we may want to suppress one of them. But the bottom line is both the imaginary and the real component contains the information that is being transmitted. So suppressing one of those components will not lead to loss of information. Okay? And then we tried to resolve some of these things while talking about the discrete time signals and the continuous time signals, right? Continuous time signals, where this is signals, and then discrete time signals. Because we could also have discrete time systems and continuous time systems, okay? And trying to analyze or better said, interpret some of these signals and the likes led us to some mathematical deductions. At some point, we used the arithmetic series, we used the geometric series, and then moved on to the manipulation of signals, okay? And then in addressing the manipulation of signals, So in addressing manipulation of signals, we moved on to talk about the scaling of signals, either time scaling or amplitude scaling. We also made mention of time shifting, amplitude, shifting. We could shift either of them, depending on what we are looking at. So when we talk about time shifting, we talked about either signal advance or signal delay, which we see often in convolution activities, because the idea about the convolution process is just to shift the signal component. That is what the impulse does, right? The impulse signal. That's what it does. It just helps us shift it in time, And then we also considered some other components, like the wave representation, how we could represent a wave. And we literally emphasize that not all waveforms can be represented using ramp and step functions, right? But for the basic signals we can represent with ramp and step functions, we came up with the rules, okay, of how we could represent the signals and then develop a system of equation for same signals in terms of manipulating those signals. And that was it for signals. And then we moved on to talk about systems. Said, well, if there's anything like continuous time signal, so any system that will operate on such a signal should be a continuous time system. And if there's anything like discrete time signal, any system that will operate on such a signal should be discrete time system. And then we equally tried to describe some other parameters or terminologies, or better still, types of systems. Okay? And in describing the types of systems, yeah, we moved on all the way from regular definition of what the continuous time systems are, which I already talked about, and the discrete time systems. And then we went on to now describe some other types of systems, okay? And in describing other types of systems, we made mention of static systems. So it means what I transmit is what I receive, okay? And then we also talked about dynamic systems. So it means what I transmit may be delayed, okay? So it means I now have to deal with the component at the instant of time and some other time. And then we talked about other interesting systems, other types of dynamic systems, the likes of causal systems. We talked about the non-causal systems. And then we talked about the anti-causal systems. Okay. And we said, well, most of the systems we play with in practice, which we try to approximate or model, are causal systems, likely because we now have to deal with our present and past values, right? So it means we are dealing with the present signal and the delayed signal. Because if we try to model a communication system, these are antennas, and then I transmit a signal. So boom, I receive, and probably that signal strays off. Okay, let's try to say, well, and the signal will receive it. But another signal bounces off and then bounces back. So it means that the time this signal we get to the receiver is going to be different from the time the direct signal we get to the receiver. But at the end of the day, signal 1 and 2 contains the same information, right? The same information. Only that this is delayed. Why this arrived earlier? So we now see that at the receiver, we now have to deal with the actual signal and some delayed component of the signal. So we say this causes interference, right? So we want to filter the interfering signals. So they are more like causal systems, right? They're more like causal, they're more like causal systems. And that is why there are times, you have something running in your mind and then your loved one calls your name. It's like you are lost in thought. Then they call again and then you regain consciousness to say, hey, so where were you? You traveled. So it means you are causal, okay? Because we're dealing with something and what was transmitted got to you a little late. So that's more like causal. And then we also talked about anti-causal system. That, well, this does not deal with the causal components of the present and the past signals, but it also relates with the future signals. And then for the anti-causal, when we have to deal with only the future signals. Okay, so I transmit now, and then it's the future signal that we'll have to deal with. So we also said that, well, I think that's that. Then we went on to also mention some other interesting systems that led us to the LTI systems. We talked about linear systems, right? And we say, well, if we must have linear systems, they must obey the principle of superposition. So it means they obey the law of additivity and the law of homogeneity. And we already said that for the law of homogeneity, it's more like scaling, which we talked about when we were talking about manipulation of signals. And afterwards, we went on to talk about some other interesting systems. So if we have linear systems, then it means we can also have nonlinear systems. Then we can also have time invariant systems and time variant systems, okay? So which are time varying systems, okay? And then the idea was to pull off to somewhere we can say, well, do we have a stable system? So I would say these are Bible stable, meaning bounded input, bounded output. Okay. So it means for every bounded input, finite amplitude transmitted, we should also receive finite amplitude signal at the output. So that's what makes it bounded input, bounded output. And now, I haven't described all of these concepts separately in terms of understanding how these concepts play out, the signals and how they could be manipulated, the systems and how they could be manipulated. Then we now went on to address linear time invariant systems. And I think that is where we stop. Now, in addressing linear time invariant systems, LTI, linear time invariant systems. So in addressing LTI systems, we now went on to deal with systems that look something like this. So we characterize this by H of t, then this is S of t, the input, then this is Y of t, which is S of t convolved with H of t. And this led us to another dimension of analysis, okay? And then we said, well, we are literally talking in time domain. But it's like, if we have to play with some of these things in practice, it's easier to relate with these activities in the frequency domain. Okay, so how do we move all of these system analysis from the time domain to the frequency domain? Then we now talked about transforms. Okay, that brought us to another interesting concept. And in literally analyzing LTI systems, we looked up different ways we could model these LTI systems using differential equations. We also talked about the graphical approach, where we'll have to use the integrator adder and gain block diagram. Then we also talked about state space models, you know, and from the state space model, we now moved on to describe if having gotten the state space representation in matrix form, now what else can we do? So there we saw that, well, with the state equation, we can actually tell a whole lot if we are able to pull the system matrix A from the state space representation. And with that, we can check if the system is controllable and if it is observable, okay? And then we now, well, moved on to say, well, from these two, we could also talk about the stability of the system. We don't just want to develop systems that are not stable. So if they are not controllable, if they are not observable, then it means they won't be stable, yeah? So, and then we talked about different kinds of stability. Stability could be asymptotic, it could be marginal, and it could be unstable, right? So now after describing all of these things, we now moved on to talk about this impulse response itself and convolution. So we spent a little time talking about what the impulse of a system does and how to analyze these systems when we talk about the convolution process. And we also played with quite a number of activities. And then we also mentioned that we have continuous time systems and we also have discrete time systems. Okay, so could there be any approach that could be used to convert continuous time systems to discrete time systems? Now, this is not the same as transforms, but transform techniques also applies, okay? Because the methods literally thrive on transforms. And then we talked about 3 techniques: the impulse invariance method. Then we also mentioned the backward difference method. And then we also mentioned the bilinear transformation method. And afterwards, we literally concluded our talk of on convolution, and also mentioned if we have two triangular functions, for instance, of the same duration, for instance, where T1 and T2, T1 is the same as T2, then the convolution of these two functions will give us a triangular function. And if T1 is not the same as T2, then we are going to get a trapezoidal signal function. So meaning T2 is something like this, okay, with a different duration. And then we talked about, that's the convolution, when we talked about convolution process. And then we mentioned a few interesting properties about convolution, the associative property, or you could call it associativity, distributivity, commutativity, linearity, time invariance, and some other interesting things. Then we solved a few examples and also played with the discrete time convolution, okay? And we have some examples also. And then this led us to transform. So if it's easier for us to play with certain activities in the frequency domain, then what do? We want to transform so the frequency domain. And this is where we literally concluded our topic or our discussions, where we now have to talk about the Laplace transform, the Z transform. The Laplace transform is for continuous time. The Z transform for discrete time. Then we also talked about the Fourier transform, FT. Then we talked about Fourier series. And then we said, if we have to take the Fourier transform of a periodic signal, then it reduces to a series, right? So we now have to talk in terms of series. And then we also have the discrete Fourier transform, okay? Because the Fourier transform itself is for continuous time, while the discrete Fourier transform is for discrete time. And then we have a faster algorithm if we don't want to use discrete Fourier transform, which is fast Fourier transform, okay, when it comes to signal processing. So we were able to play with the formulation of all of these transform techniques. And then we solved a few examples and, decided to put a hold on what we have to discuss. We talked about a few things, okay? When we talked about Fourier series, we did mention quite a few details, despite solving some interesting examples. We didn't just solve examples, we literally described some interesting concepts while detailing some of those activities. Okay, and I think there we also mentioned that, well, there are some conditions that should be met, okay? Let's say some necessary conditions which may not be sufficient, but they are necessary for us to have, for a periodic signal to have Fourier series. And there we said, well, those conditions are the Dirichlet conditions, right? So we did mention 3 of them, that, well, the signal must be absolutely integrable, okay? So it means if we take the integral over one time period of the mode of the signal, the t, then it should give us a finite value, okay? And then that's one of the conditions. So the signal should be absolutely integrable. And then we also mentioned that the signal S of t should have finite number of discontinuities. So if we have a signal, say this, so over one time period between this point and this point, we have 1, 2 discontinuities. So this is another time period taken off from there. So, and also they should have finite number of maximas, okay, and minimas. So this is 1 and this is 2, oh, this is 1. So 1 maxima, 1 minima, right? So, okay, so those are the 3 conditions which are necessary, but not sufficient, okay? But they are necessary for the periodic signal to have Fourier series. And then we also talked about the Passavas theorem, which tells us that, well, the energy content of the signal when it is in the continuous form is the same when we transform to the discrete form. So nothing affects the energy of the signal. So if we try to talk about the signal in the continuous time domain or continuous, if we try to talk about a continuous signal, let's put it that way, and then transform that signal through sampling to discrete signal, there is no loss of energy content of the energy content. So the energy content remains the same. That is the energy signal of the continuous time signal, the t over 1 time period, is the same as the energy signal in the discrete form. Okay? Say when n takes some values from negative infinity to positive infinity. And I said, this is what we call the Passavas theorem. Okay? So just in the flash, we just reviewed everything we've done in this course. And then the big question that follows is, and so what? What then can we do with this course? So that is why we want to talk about the application. Yeah, interestingly, we just ran through the introduction. But what I want you to understand when it comes to application is that the engineering core principles depends on signals and systems for their understanding. Now, regardless of what you want to study, be it civil engineering, mechanical engineering, aeronautics, whatsoever you may call it, okay, it's either we are dealing with systems, you consider bridge work. It's a system, okay, because that bridge is more like a system that is going to bear load on it, okay? And so we can literally call the load on it as the signal, okay? So if it's not strong enough, if the strength is not sufficient to bear the load, then that will lead to system collapse. So everything from medicals to biomedicals to engineering to science to nature, even to existence, all we try to relate to it is signals and systems. Okay? And once you understand this idea, understanding every other thing about life becomes very easy. Okay? Even to your decision making. So, technically, we are saying that the technology behind signals and systems applies in diverse industries, okay? And platforms, walks of life, okay? And these principles could be applied also in electrical engineering, computer engineering, systems engineering, and biomedical engineering, being the coverage for this course, okay? And what are these applications? So I'll just mention a few. Now, first of it is signal representation. So we could talk about different kinds of signals. Voice signals, video signals, data. They are all represented mathematically for transmission, right? And so we could talk about your regular analog signals, okay? These are voice signals, which we try to convert to digital formats using sampling and quantization. And the digital signals are equally modulated and transmitted through channels. And then another interesting application is modulation techniques. So we have your angle modulations, and we have your digital modulation schemes. We have amplitude modulation, frequency modulation, phase modulation. We have phase shifting, quadrature phase shifting, quadrature amplitude modulations, a whole lot of them. Now, they all thrive on the principle and discipline of signals and systems. Now, one thing we try to deal with, those of you that do machine learning, that do artificial intelligence, and a whole lot, is noise. We want to do noise reduction, right? So it all rises and falls on the discipline and principles of signals and systems. Because here we want to figure out how to design filters. Now, and we mentioned in our lecture, these filters could be low pass, they could be high pass, they could be a band pass, even band stop filters, okay? So depending on what kind of filter, and then we could use some mathematical models for those of you that will go way into filter design. It could be, we could use a Chebyshev, Butterworth, even elliptical model to design any of these filters. So we could design a low pass Butterworth filter or a high pass Butterworth filter, depending on the application. We're going to see how some of this applies. We're going to run some algorithms. So talk about your mobile communication, talking about 6G now and the next generation technology, 5G, 4G, 3G, 2G, whatsoever technology you're talking about, internet protocols and the likes. Then in your control engineering systems, we're talking about feedback control, right? Talk about feedback. Okay. And why do we have feedback in systems? So I want to transmit this, and then it's supposed to go all the way to my output, but I want to be able to control my output. So, and I have to feedback my expected output, so we're able to control the eventual output. So these systems, and we apply this in so many applications, either robotics or whatsoever. System stability is also part of it, and a whole lot of applications, you know. We can also move to the biomedicals. We have this electrocardiography, that's ECG. We have magnetic resonance imaging, your MRI, your brain-machine interfaces. They all are designed and developed going by or based on this discipline. Then you can also talk about your power systems, right? Power systems. Talk about load balancing. Okay, so you want to analyze load, you want to analyze power consumption and see how signals could be optimized for load distribution across grids and all of that. Fine. Also, in power systems, harmonics and filtering. Okay, so you want to analyze signals in such a way as to improve the quality of that signal. So you're analyzing for harmonics, right? So even in machine learning, okay, now machine learning, okay, we have feature extraction. We have pattern recognition, and so many other applications, okay? So the list, I'll say, is endless, okay? And then in driving these applications, what are the basic tools we want to adopt? Your transforms, right? Fourier transform, your Laplace transform, your Z transform, and also convolution. So these are the basic tools. So now for your Fourier transform, we already know you want to convert signals from the time domain to the frequency domain, and they're largely because you want to analyze signals and also design filters, right? And soon you realize that the channel is usually modeled more like a filter because it is acting on the signal. Okay, so and then when you want to model a system, you now want to model that system like a filter. Okay, because so anything that can take in input and produce an output is more like a filter, right? Yeah, so more like that's more like the discipline. Now, for your Laplace transform, here you can literally simplify continuous time signals and then transform to your frequency domain and then use this to control systems and circuit analysis, right? So you want to control systems and perform circuit analysis with your Laplace transform. Why your Z transform applies to discrete time systems. And this also is used to analyze sample data, right? To analyze sample data. So we want to use this in signal processing and control system. Why for your convolution, we literally use this to determine the output of LTI systems, like I mentioned earlier. And then we also use this for image processing and for filtering. Because the bottom line is any box that we could call a system that is capable of taking in an input and then producing an output that may be the replica of the input or a distorted version of the input is more like a filter. Okay. So now that we have looked at all of these, I think now let us move to a different platform. Let's see how we could literally play with some of these activities in MATLAB. Okay, let us see how let's see how this plays out in MATLAB. So now these are some programs. I'll just run through them briefly before we call it a day. So let's start from simple audio processing. Okay, this audio processing. Now, in this case, I have an audio file, which is a WAV file. So hope you can see the movement of the cursor, please. Can you see this? Are you still with me? Okay. Now, this is an audio file, okay? This is also an audio file. It's a WAV file because we want to analyze the signal and all of that. So probably you have your MP3 audio file, and then you want to convert it to a WAV file. And once that is done, we now see that this is just a simple program, and it calls my audio file. Now, my audio file name is audio_sound.wave. It could be any name. And then, so this is just to say audio read. I want to read this file, right? This is what I want to read. Boom. So that once I run my program, then I should be able to read this file. Now, did you hear the sound?
No, sir.
No, you didn't hear the sound. So I think I'll have to do something about the video settings. Oh. Okay, so, well, let's clear this. So the idea now is, well, I want to read this file and I want it to sound, right? So that's why it's sound, but I filtered it, but I did not display the filtered signal here. So if I should run, and then that should give us. Now, the next thing here is that I want to show up the spectrum of the same audio, okay? I want to see what the spectrum looks like, then I want to filter it. But this time, I'm going to define the cutoff. So the cutoff here is 2000, right? So, and then see if that will happen. And what filter are we using here? We are using Butterworth filter, right? So I'll show that to you. So that's to plot the spectrum. And then this is a low pass filter, and we are using a Butterworth low pass filter, okay, for this design, okay? So, and well, we are still going to confirm the difference between these filters, okay, in terms of filtering this audio signal, because this is literally, we just want to do audio processing. So let us run this and see what is going on. Go. Now, you see that this is the original spectrum, and you see that this spectrum literally extends. Let's make this bolder. It literally extends all the way, and you can see some of this, the amplitude. Now, we cut this off at 2000, so you can see at this point it's smooth, right? It's somewhere around here is 2000, this 5000. So this is what we're going to do now. We're going to close this, and then let's try to sample this at 200. Let's see. Let's reduce this to 200 to save, and then see if it's going to cut off. That's it. Boom. Now, did you observe any change in the intensity of this song, of this sound?
Yes, sir. It was
quite...
Absolutely, because with the low pass filter, we've literally cut off the high frequencies at this point. Now you can see that this is the main signal. So we've literally performed filtering here and cut off at 200. So you see most of these components are no more present in this signal, okay? You see all of these components from this axis also have been filtered out. That is what we have here, okay? So what are we literally doing? These signals and systems, all in practice. Okay, now this is a list of what we could do, really, the list of what we could do. But let's look at, well, I really do not want to bore you with all of the MATLAB coding and all of that, which is expected as you progress, okay? But nonetheless, let's just see if we'll be able to have a nice time today. Now, I want to do something about this. So I want to process the amplitude and then do some frequency activities here. So let me just run this. Okay, I can see one hand up. Go ahead, please. Godwin, go ahead.
So please, the screen is not clear.
Okay, the screen is not clear. Are you sure?
Yeah, you can't see. You can't see the code.
Is it a general thing, or could it be network from your end?
That's a general thing.
Same here. Same here also.
Okay. Wow. Okay. Well, nothing to worry about. Since I'm recording, I'm going to upload the video, and I think it should be clear from my end. Okay. Okay. So I think if it's not the bandwidth, then now here I'm still, going to do the same thing, but now I want to return my amplitude and phase values. So let us run. So we can see, the amplitude and phase plot of the original and after filtering. Well, if we have some time, I will say explain, but I have quite a couple of things I need to show you. So now I don't just want to do this. I also, now you see that in this case, I've equally generated the filtered video. So now this wasn't here before, right? So I've generated a filtered video. So, and I remove that, let's remove that. And then let's process again. Now you can see I just created a filtered video. So I wanted to look at this. Now I'm going to delete this again. So I wanted to look this up. Can you see this part of the screen, please? Are you still with me in class? Can you see this part of the screen, the highlighted part?
Yes, sir.
So I want to delete it because now we want to filter the video, the audio, and then have a copy of that audio file, the filtered file. So this code literally does that for me, okay? Because I want to do audio write. So in other words, once I do audio write, then I need the filtered video, the filtered audio, okay? So I want it to generate that for me. So once I run, now you see we have it here. So with the code, I've been able to both filter the audio file and also generated a copy of that filtered audio file, right? Okay, so I'm going to take this out again. And then I can move on to the next. Now, I think here, I don't just want to do all of those filtering. I want to also generate the data, okay? I want to pull the data of whatsoever I may have generated, okay? So I need the program to run that. So now you see that here I have literally done my filtering. I have my amplitude and frequency spectrum. Then I equally have the Excel file showing the data. So let's open this and see what we've got. Let's see what we've got in the data. So let's assume I need the raw data to do one of two things, right? So probably I want to use it as my data set. So you now see that from what we've got, let's take this out. So you can see the frequency and the magnitude values. So you can see that's quite a lot, over 23,000, no, 233,000 data points. Now let us check the amplitude because we literally requested for the frequency data plot and the amplitude data plot, right? So, boom, that's it. So we've got the data plot. So you can do a whole lot, okay? Depending on what you want to do. And here you see that I did not sound my data, you know, and all of that. We'll come to that. Don't worry. Now, the next thing I also want to show you is on the use of different filters, okay? So I commented out the sound. So I don't want to play the sound, okay? Yeah, but I can uncomment that. But this time, I just want to play with some other low pass filters. We've been looking at Butterworth alone, right? So what is going to be the response of Chebyshev low pass filter, type 1 and the type 2 Chebyshev low pass filter? Then how about the elliptic low pass filter? How would they behave, you know? So which would be better? So we want to know the best filter to use for filtering this audio. So once I run this, so this is what we get. We get this response. And now we can see the magnitude plot for all of these. And then we now want to interpret this and see that, well, some are smoother than some. Okay, so I'll take a little time to explain how all of this works. But let's just show this first. Then, so which of them haven't we? So we've just played with okay. Okay. So now I want us to look up the response of the different types of filters, right? The frequency response. So this is what we got before. So we have the original audio file. Then when we applied Butterworth filter, low pass filter, the Chebyshev type 1 low pass filter, and the Chebyshev type 2 low pass filter, and the elliptic low pass filter. And now you observe that the Butterworth filter seem to have a very smooth response, right? You can see this. It's smooth, smooth, smooth. So the magnitude response is, is smooth, and the roll-off is pretty smooth with no ripples, okay? And why should we have ripples? Now look at this. Let's look at this elliptic filter. You can see we have ripples here. Now, why do we have these ripples? Now the Butterworth, Chebyshev, and elliptical filters are designed based on some mathematical models, okay? So we refer to this as interpolation or approximation of functions. So depending on the approximation method used, that will determine how smooth the roll-off will be, okay? So that is why the Butterworth filter is usually preferred for audio signals, for audio signal or speech processing and all of that. Because if you also look at the phase frequency, there's a gradual phase shift, okay? And it's almost linear. Now, if you look at the pass band, this is the pass band. It's almost linear, right? So, which is good for audio filtering. And then that's for Butterworth. Let us see. This is Chebyshev type 2. Let's look at Chebyshev type 1. Okay, that's that. Let's look up. Okay, this is Chebyshev. Now, you see for the Chebyshev type 1 also, we have something also close to, oh, what happened? I stopped sharing. So we probably have something close to the Butterworth. See that? So for the Chebyshev type 1, well, you'll see that the roll-off is kind of steeper, but it's a little steeper than the Butterworth. But here, for more complicated systems and designs, we experience some level of ripples also, okay? And then for the type 2 Chebyshev filter, we can see, well, a lot of ripples here, right? Now, and which is really not desirable, okay? Yeah, we don't want that in our system design, really. So,
Sorry, sir. Did you say there was a ripple in the Chebyshev type 1?
No.
Okay, I wanted to be
I
sure.
mean, this Chebyshev type 2, this type 2. This Chebyshev type 2. This is Chebyshev type 1. It's something close to the Butterworth, right? Okay. But if you look at the phase plot for Chebyshev type 1, is steeper than Butterworth. You can see that here. Can you see this? Can you see the cursor move, right?
Yes, sir, we can see it. It's steeper compared to the Butterworth.
Exactly. So you want to make your choice relative to some of these metrics, okay? And oftentimes, well, the Chebyshev type 2 and Butterworth are, well, somewhat preferred. for audio processing and all of that. Well, that's about that. So now I think that's enough for our audio processing. Now, how about image? I know most of those of us in biomedical engineering will do a lot of image processing and all of that. So here I have a plant file, a PNG file. It could be JPEG. So let us do edge detection. Okay. So normally when you want to do your image processing, you want to do feature extraction. Then afterwards you want to do the edge detection using some algorithms, and then you want to do segmentation, recognition, and all of that. So there are some, traditional algorithms, which I don't want to go into. When you advance it, when you move way into your program, then you want to begin to talk about some of those traditional algorithms. And then we now realize that the machine learning based algorithms perform better, okay, in terms of these feature extraction and all of that. So let us look at this. So this now, I'm going to run this, and then this literally telling, just like we had audio read. So this is going to say image read to read my plant file, and then we try to do some grayscale image activities for edge detection, and then we plot. So let us run this. Boom. Okay, so that's what we got. Okay, so this is what we got for this. So I don't think I would have probably taken us way into segmentation and recognition and all of that. So where we now have to play with probably let's play with some of the machine learning based algorithms. But I think that is not the essence for now. So the only thing we are trying to push here is that as abstract, a couple of details we may have been relating with may be the beautiful thing about the signals and systems ideology is that we are able to interpret our signals, process the signals, and get the desired output, okay? So you now see that the bulk of what you guys now do in your computer vision and image processing and the likes, they are all products of signals and systems. So this is more like building the foundation for your study. Is that okay?
So I have a small question too.
Okay.
When we were doing this, and I noticed that
When we're doing what?
when we're looking at audio processing, the frequency of the signal like corresponded to the pitch. Like when you cut off higher frequencies, I didn't really hear as, and I don't think I heard high pitched sounds anymore. Well, in image processing, what does the frequency usually represent there?
When we have to play with the frequency values for the image, what we are particular about or dealing with are the pixels. Meaning we are particular about the rate at which these pixel values are changing.
Applications, signals and systems.
Does that make any sense to you?
Yeah, I have an idea.
No, because if you look at this now, you can see all of these dots, right?
Yeah.
Yeah, those are pixels, and they have different frequency values. And when we use machine learning, we want to be able to interpret them better than this. Now, this Sobel algorithm is a traditional algorithm, okay, for edge detection. So what is literally trying to do here is to analyze these pixel values within the spatial domain. So I'm literally mapping this with respect to their location. Okay?
Did you didn't get the last part? You said you're not going to this.
Now what I said is, okay, I think Oye Kale is, okay. Now, what I'm saying is that these pixel values are mapped to different frequency values. Okay, and these frequency values are mapped with respect to their location in this image. So while in your audio, we're talking with respect to the time, here we are talking with respect to the space, the location. Does that still cut it for you?
Yes, sir. I understand it now.
So what we are just what I'm trying to say is that word pixel, like where's my is your frequency for image or images. Because what we are considering is the rate at which the intensity of these pixels are changing, and that is your frequency. You get what I mean? So you see there's a variation. Now, this is a tree, right? This is the trunk or the stem here, this part, all of these. Okay, now you can see the variation here. You can see we can just spot a few dots here, but we don't have anything here. We have a few dots here. So the rate at which these pieces are changing, you know, tells us the frequency. So what I'm trying to say is that the rate of change of frequency of pieces literally tells us the frequency, right? I don't know if this cut it for you, you know. Is that clear?
Yes, sir. It's fine. It's clear.
So any other question, please? Any other question, please? Okay, so if there is no other question, I think we'll say this is where we wrap up for the semester, and hope to see you when you resume on campus. Okay.
Thank you, sir.
Thanks, sir.